Hello, welcome. My name is Adam Bernot. I work at Google Cloud on the Google Cloud Managed Service for Prometheus.
Hi, my name is Bryan Boreham. I am a distinguished engineer at Grafana Labs. My day job, I work on massively scalable storage for metrics, logs, traces, and profiles. I'm also a Prometheus maintainer, so if you like that.
Yeah, and feel free to follow us on our Blue Sky handles that are listed on the screen. We'd love to connect with you if you find this talk entertaining. We're going to be talking about how DaemonSets run in Kubernetes and how to use autoscaling to make them more efficient and more effective.
Yeah, so show of hands, get a bit of audience participation going. How many people have used a VPA, a vertical pod autoscaler? Okay, so that's about maybe a fifth of the audience, something like that. And how many people have used a DaemonSet? Oh, nearly everyone. How many people have used a VPA with a DaemonSet? Yeah, that guy. Well, that's what our talk is about. We're going to kind of motivate the problem that we see with this, and then talk about what we did to try and solve it, and hopefully give a demo.
Yep.
And we're the second last thing between you and free beer, so just chill, stay with us, and we'll take you on a journey. Oh, yeah, picture. Okay, demons. Demons are not coming from hell. What we mean by demons here is a computer program that runs in the background. And apparently this comes from Greek mythology, the idea of a demon being a kind of generally helpful thing that hangs out and does things for you. In Kubernetes terms, a DaemonSet will run one pod on every node in your cluster. And why would you want to do this? Well, something like a network controller that needs to run on every node, that will run a DaemonSet. Logging daemon, something collecting logs from every node, that will run metrics collection on every node. Is this kind of thing that we're talking about. That's what you would use a DaemonSet for, and they need to run everywhere.
Yeah, so just a little bit more level setting before we get into the meat of the talk. But let's talk about resource requests for a second, since we'll be talking about them throughout. When you set up anything to run in Kubernetes, you can specify how much CPU and how much memory it will use. The Kubernetes scheduler looks across the available nodes and picks a node where your workload will fit. So these resource requests are important in the scheduler being able to do its work effectively. Specifying requests is optional, but it's highly recommended, as you'll realize as we talk through some of the implications in just a moment. So our fundamental problem is this. Imagine you have a cluster where you have perhaps some small nodes and some big nodes, and you're running a DaemonSet, like a logging collector, like a metrics collector, something like that, where the work that your DaemonSet is doing depends on the other work that's happening on the node. So you only get to pick one set of requests that will apply to all of the pods under the DaemonSet. How do you decide the correct request to make? Before we answer that, let's consider the consequences if you're wrong. If you pick a limit that's too low, the pod might be starved for resources, or some of your pods, or all of your pods. For CPU, that means the workload gets throttled. For memory, that means that the application can encounter an out-of-memory error and crash. That's not great. If you pick a request that's too low with a high limit, the workload can misbehave or become a noisy neighbor and interfere with other workloads. and here be dragons. There's kind of unpredictable behavior when your requests don't match your actual usage. You can also run out of capacity at the container level or for the entire node. In either way, the consequences are similar. For DaemonSet in particular, if your resource requests are much too high, some or all of your pods may become unschedulable. So in this example, you might have a large node that wants more resources than some of the small nodes have to begin with. So that obviously won't work.
Yeah, so if you, on the other side, if you put the request much higher than you actually need, then you're kind of wasting that resource. It can't be scheduled for, it can't be allocated for other pods on the system. So you have this terrible choice, right? If you go too low, you might get throttling or crashing. If you go too high, you're wasting money.
Yeah, in the particular service that I work on, the Google Cloud Managed Service for Prometheus, it runs with high priority class because we want to prioritize collecting metrics. And so over-provisioning can also lead to user workloads being evicted. So in that case, the Prometheus instance that's running will start to take up more and more resources and push out the workloads that our customers actually care about. And if this gets really bad, you might not be able to schedule any user workloads on some nodes. So obviously, that's not a good situation to be in. You don't need to collect metrics from nothing.
So I wanted to bring some real data. This is a logging daemon running in one of our dev clusters at Grafana Labs. And so these are the actual CPU usage of a set of about 15 pods that they're all the same, but some of them are doing more work than others. So yeah, the question is, where do you set the request?
So your first option is YOLO. If you don't set resource requests at all, you're likely to have your workloads eventually misbehave because the scheduler is missing some of the information that it needs to be able to schedule workloads appropriately.
It's very popular, though, right?
It is very popular, from what I understand. There are certain platforms, like if you're running on GKE Autopilot, for instance, where the requests are actually required, and it will set a default value for you if you don't set them yourself. So this is not even an option on certain platforms. Another potential approach is a conservative approach, where you set your request high enough to cover every instance. As I mentioned, this can have some problems if there's not enough available capacity, but you're also wasting resources. So in this example, if you set your request to the highest node, you're going to have all of that empty space under the purple line is going to be wasted capacity that you're paying for, but you're not using. A third option is being very aggressive. You can set your request very low and allow bursting and hope that there's resource capacity on the node. In this case, you end up with a different kind of problem that's similar to the issues with the YOLO approach, where you've set a request that is inadequate and you might not have space reserved for the workload that you need. A fourth approach is divide and conquer. You can divide a daemon set into multiple daemon sets and set requests and limits for each sub-daemon set. In this case, you limit the blast radius of your over and under provisioning issues. However, within each set of pods, you still have some of the same problems. So in the example on the far right, you're still seeing a lot of wasted capacity within that subset, for example. Also, this becomes more work intensive. Each subsequent update requires you to update multiple resources, and you start undermining some of the value of the DaemonSet controller. You have to make sure that your node selectors are appropriate and that you don't have overlapping groups or that you're not missing things from your selection groups. So it becomes much more tedious to try to manage this. But what if there was a way to automate away your problems? That is, instead of trying to manage multiple daemon sets yourself, what if we did the hard work for you?
Yeah, so let's get into a little bit more detail. The vertical pod autoscaler. So most of you did not put your hands up as having seen this, so let's just talk about it a little bit. So this is the YAML to define a VPA object. You basically point it at a set of pods. In this case, I've pointed it at a daemon set, which is the Grafana logging daemon that we're going to use in the demo. You can add more parameters. You can set a minimum and a maximum, and you can set policies and things like that. But that's the basic idea. You define one VPA object that points at the pods that you want to control. It then runs as 3 processes. So let's just walk through those. The top one is the recommender. So this watches the actual resource usage of your pods, the ones you told it to control. That's defined by the VPA object. And it also writes a recommendation into the VPA object. The next one is the updater. Who knows what the updater updates? Yeah, it's a mystery, isn't it? It's a trick question. Doesn't update anything. What the updater does is evicts a pod that is out of range. I didn't actually know that until I started working on this project, but here we are. So the third process is an admission webhook. And this is something that runs as the pod is created. It gets called from the Kubernetes API server. So as the pod kind of flies past on its way to being created, the VPA admission webhook applies the recommendation. So this is why evicting works, that we kick the pod off wherever it's running, modify its request, and it reappears. So a little dance. And that's how the current VPA works. So we'll get into how we modified it.
Oh.
Yeah?
Yep. So in some of these cases where one size does not fit all for your requests, we propose that instead of applying a single recommendation across the entire daemon set, that we create a customized recommendation for each pod scheduled on each node. So by adding a scope field to the vertical pod autoscaler spec, you can specify how you want the VPA to behave. In this example, we use the Kubernetes hostname to declare that it treats each pod with a unique hostname, effectively the pod on each node, as its own unique scope that gets its own recommendation based on only the history from that host. So I'll turn it over to Bryan to show you how this prototype works.
Yeah. So we have a demo environment, which is a 3-node cluster. It's running in kind. At least I hope it's running. We'll find out in a second. So we have a 3-node cluster, and we have a monitoring stack, and I'm using Grafana Cloud for that. So we're sending metrics and logs and so on. And we're actually going to use the logging daemon as our guinea pig for the test. So let's see if I can make the demo appear. Okay. Okay, there's one. Okay. Not too bad, not too bad. I should just stop the demo there, right? Let's not tempt fate. How are we doing for time, actually? Pretty good, pretty good. Okay. So, let me see if I can run commands. Yeah, OK, there's my 3-node cluster. So we are looking at the CPU usage is the thin line, and the request is the thick line. And it's sitting, it's not doing much right now, right? Because it's just a kind of empty cluster. I could show you that. So basically, the only things that are running are the kube system pods and the observability daemons. So I'm going to introduce some load. I'm going to run a pod that generates some logs. Now, well, let's just see if that's running. What happened? Oh, -F, thank you. Everyone's screaming at me, -F, -F, -F. Shows you it's a live demo, though, huh? OK, so the VPA by default might take a couple of hours to kind of think about its recommendation and apply it and so forth. And we don't have that long in the system, in the talk. So I have modified the settings of the VPA so that it's going to react a lot faster. So there's the load coming in, right? You see that I'm only running the load on the right-hand node. And it's generating logs, so the logging daemon is having to do more work. So what I'm hoping is, there you go. So the VPA has recognized that the load on that pod was higher and has evicted it and has applied a new recommendation which is higher while not changing anything on the other 2 nodes. There we go. So yeah, there's like a burst of CPU as the thing takes off, but it'll hopefully stabilize about there for long enough for me to get the slides back up. Anyway,
yep.
OK. Where are the slides? OK. Is that going to work? No. Yes, maybe. Whoa. OK. Yeah, just like talk amongst yourselves. Right. There we go. OK. Thank you. Right. So we demoed modified VPA. Thank you. We demoed the modified VPA. We demoed it reacting to increased CPU usage on a per node basis, and that is with this field in the VPA called scope. So I guess you're wondering, how can I get my hands on this?
Of course. So currently, I have a autoscaling enhancement proposal that's open, and it's under active review. And the code that you just saw for the demo is linked within the proposal, and we'll give you a direct issue or a PR reference at the end of the talk here. So there's a few phases before this will roll out into general availability. But the next step will be the approval of the proposal after we get all the feedback we need, and it's reviewed by the SIG Autoscaling and the folks that are reviewing the proposal. Hopefully that will be approved. We'll begin to develop a more robust implementation and work on solving some additional problems related to scaling and production readiness to make sure that this will work effectively anywhere it might be deployed. So with this feature, we hope that we'll both reduce wasted resources and cost, due to over-provisioning. They will be able to mitigate stability problems associated with bursting. And we would love for you to get involved. You can find the proposal on the Kubernetes Autoscaler repo. That's pull request 7942. And the prototype code is also up there. It's PR number 7978. And you're welcome to visit my blog as well, where I have a short write-up of the problem that we're trying to solve. With that, we'll turn it over to questions. Thanks. Please approach the mic if you have questions.
Yeah, microphone is kind of front and center.
Hi. You showed the demo, and in that, we see a spike of CPU when the new pod is created, right?
When it was restarted, it spiked, yeah. Exactly. And that's basically its initialization, and because it's a logging daemon, it kind of rereads the logs to catch up to where it was before.
Exactly. So how does it know that that's just a spike of the restart of like it catching up and not like a general load, right?
Yeah. Well, so yeah, it's a great question. So the VPA already, the way it works already is it's capturing a histogram of CPU usage, and it is applying a decaying weighting to those samples, and then it takes a 90th percentile. So basically, you would expect, under normal circumstances, it would ignore a quick spike.
And is there like a configuration so you could actually change it for specific types? So for example, my pod starts up with like extra load for some reason, right?
There's a lot of configuration on the VPA. I'm not sure that you can do much about. I mean, you can configure how long the exponential decay is and things like that, but that's the basic behavior of it. So if you want a radically different behavior, you might need to find some other project.
It will depend a lot on your workload as well. If you know that there's going to be an initial spike and then it will settle into a different value, you might want it to react more slowly. If you know that initially it's going to keep handling the amount of load that it is, and that is immediately your steady state, you might tune different options.
Yeah, thank you.
You're welcome.
Hey, so what happens if you are approaching GitOps? Meaning, for example, I have Argo CD, and it's always monitoring my cluster, and VPA comes in and change some of the resources, which is not in my Git repository. Argo will just go and run it over. So
do you want to take that one?
Yeah. So the way that the vertical pod autoscaler works, it's not actually changing your initial resource. So in the example of a DaemonSet, it doesn't change the spec of your DaemonSet. It just modifies the pod at the very last moment with the admission webhook. So the DaemonSet is responsible for creating a pod, and just before it creates the pod, it asks the VPA, oh, by the way, how much CPU should this have, how much memory it has? So you would not expect to schedule individual pods under a DaemonSet in your GitOps, if that makes sense.
So essentially, it's just like a quick solution for a local problem.
Quick solution for a local problem. I'm not sure I understand.
Meaning,
So if you want the changes to be written into Git, then this is not a solution. The way the VPA works is it modifies the pod requests on the fly using an admission webhook. That's the way VPA works.
Okay, and second question, does it take into consideration cube reserved and system reserved?
Does it take into
Kubernetes takes those into effect. The VPA is obeying however you configure it. So you say, watch these pods and make a recommendation within these bounds, using this policy. It doesn't really care about the system request and anything like that. Those are handled by kubelet.
Thank you.
Hi, first of all, great feature.
Thank you.
The question is, when you've been developing that and playing with different daemon sets, have you encountered a problem where your default memory CPU, or mainly memory request, was too low for some big nodes, and the VPA was not able to catch up and recommend a new memory because it was constantly crash looping?
Yeah, so the VPA doesn't really care about the initial request. Once it makes a recommendation, it'll do so because it has a confidence interval that it feels good about it. Some of those options are tunable to some extent, but if you're just using out-of-the-box VPA, it's going to be fairly conservative, and it's going to try not to cycle your pods more than it has to.
So there's one exception. If you're actually getting out-of-memory crashes, it increases more.
All right.
Yeah.
So there's special provision in the code to watch for events.
Okay, that answered my question.
And all of that's in the VPA already. So
yeah, that's not a new feature. It's existing functionality that will be included.
Yeah, no.
Yep.
Cool, thanks.
Hi.
hello.
In your demo, how the new logging pod knew where to catch up on logs compared to the previous one that got killed?
How did it know to catch up on the logs? I mean, that's what logging daemons do. It writes out a snapshot periodically of where it got to.
But let's say it got killed writing log A.
Yeah.
How does it know that when it restarts, it still need to write log B and not log A again? Or Grafana?
Yeah, it snapshots that information to disk so that when it restarts, it can pick that up.
Okay, so you kind of cache that information on the node itself.
On the node, yeah.
Yeah.
Yeah, it's and also I think we assume that we can resend some logs that it's idempotent. Yeah, but I mean that's just whatever logging daemon you use, it will have some other behavior. This is not really a talk about logging daemons. We just used it as a demo.
Yeah, of course, yeah.
In the more general behavior, with any workload where you expect to cycle the pods, you want them to be resilient to that. And there's some very exciting work going on with in-place pod resizes that will make it so you don't necessarily have to kill the pod every time. You can resize it without restarting it, which will be
interesting for kubeproxy, for example, if you want to apply that to critical daemon sets that you can't afford to lose.
Yeah.
Cool, thank you.
Hi.
Hello.
Thanks for the talk. I have one question on the mechanism you're proposing here. I think that works pretty nicely in a static cluster where all the nodes already exist. Did you think about how will it work when nodes are not yet there, and so there is no VPA recommendation, and the thing that is scaling a cluster needs to predict the resources that will be used by DaemonSets? So how will that work?
This is one of the issues that's being actively discussed on the proposal. There's a few different ideas about how initial recommendations should be made. And so we're definitely working on sorting that out. I think that in general, the expectation should be that once the vertical pod autoscaler makes a recommendation in this per node model, that you'll be getting the behavior that you want at that point. So yeah, there are some open questions that people are debating about what you do between the initial recommendation or the initial request and the first recommendation.
Okay, thank you.
Hi, you showed the hostname scope, but are there any plans to get more scopes available?
Yeah, I guess I put that on screen as a kind of a So scope equals instance type. So if your problem is basically that bigger nodes use more resource, then instance type looks like a more efficient, more attractive target. It so happened that this is host is the one that's in the demo, in the prototype. Instance type sounds attractive, but it's actually harder to implement. Node pool is another one that's been suggested. So scope equals node pool.
Just to clarify too, the scope is intentionally extensible. The current proposal just includes the hostname. So yeah, that's certainly an area where additional proposals could be added. We may get feedback during the proposal cycle that we want to include things initially. But yeah, we're definitely thinking about that and open to it, different subsets of scaling.
Actually, one of my colleagues wants to use this on stateful sets. But Adam's going to kill me if I say that, so I didn't say that.
Cool, thanks.
Hey, have you guys thought about how this would play with a tool like Carpenter, or if you guys have any opinions on this in terms of it Carpenter trying to right-size your nodes, and then this trying to right-size to those nodes? Would these contend?
Yeah, so I don't know a lot about Carpenter specifically, but in Google Cloud, I know that we have many autoscaling options for like cluster autoscaler and all those. So we have some of the same concerns. Yes, we are thinking about that and trying to make sure that they will behave in alignment with the general expectations of the users. So yeah, there's a lot of complicated issues that you get into when you're trying to do like multi-dimensional scaling in several ways. And we've run into some of those already without the prototype. So an interesting space. And if you have comments, please get on the proposal and let us know.
Cool, thanks.
Hi. You mentioned at the beginning of the demo, VPA normally runs over a long period of time, like I think you said hours, and that you lowered it down. But for these daemons, like a lot of their load is typically driven by what happens to land on the machine. So suddenly some pod, a lot of logging or a lot of proxy requests to a proxy, 2x its capacity. And so I guess my assumption would be you generally want to run VPA for daemons at a faster rate. And I guess I'm wondering why wouldn't that be the default, or what are the risks of doing that?
So there's a few mechanisms that you can use to respond more quickly. So one is that if you're anticipating a memory spike and you hit your request and limits are close, you might hit your memory limit and you get an out of memory error, and then it'll apply a new recommendation quickly after the pod crashes. In CPU, you can again, kind of toy with your requests and your limits to know what you want, what behavior you want. And then, of course, you can also tune the recommender to behave differently or respond more quickly. I think, in general, there's a lot of work in this space right now with the in-place pod resize that will change some of the assumptions about how quickly we want to respond in general. Because up to this point, the assumption has been to make a new request, to set a new limit, you need to kill the pod, and that we shouldn't just kill pods for fun.
I was also just curious, are there internal scaling limits if you start driving VPA recommendation more quickly that you'd have to be concerned about, or is it primarily around more of the mental model for
Yeah. So
I would be worried about the amount of resource the VPA itself would start to take if you try to drive it really quickly and make it really clever.
Yeah, it's pulling information from the metric server or from Prometheus, and so it does have to gather the usage regularly. So if you start to tune that really fast, you're going to run into problems.
But it's an interesting space. I mean, we're here to kind of talk about future directions and experimentation and so on. We're not claiming to have solved all the problems. So
yeah.
Cool. Thank
Just
you.
a specific one.
Thanks for this, actually, because it's a big issue where I work at. My own case was more on the scope field. Like, is there like a plan to extend like it from being just like a string to being like the anti-affinity kind of definition, like more like broken down in that sense? Because there are some like high priority nodes you might just want to skip doing this on.
There's definitely opportunities to extend, and we're out of time, so I'll have to cut us short before we get to the last questions. But yeah, there's definitely some opportunities, and please jump on the proposal to comment. Yeah. Thank you.
Yeah, I guess we're out of time, right?
Yeah.
Thank you.
One last question.
Yeah.
Come up
I'm
to the
happy to
front
speak
and
with you
ask.
at the front.